Okay, good morning, good afternoon, and good evening to the friends everywhere. I hope you and your family are doing well in this special time, and we hope everything will become back to normal pretty soon. So the topic of my presentation will be advanced lithography for optoelectronic nanochips. Actually, this is the name for my own research group. I just made it special alien. It means I want to do something special and very different with others. And these are the devices we're going to talk about today. Okay, so before everything, I would like to thank my postdoc supervisor, Professor Lithography at New York University. Without her, I wouldn't get anything. I mean, the position, everything, all this work has been done under her supervision. So it's great honor for me to work with her in her lab. Okay, a little bit introduction of my Westlake University. Is located in Hangzhou City, and this city is in the southern east of China. And if you look at the location, it is very close to almost everywhere. You step on the fast-speed train. After 45 minutes, you can go to Shanghai, and you can go to other cities, main cities in the world. Okay, and you can enjoy a very different lifestyle in Hangzhou. Whether you like history or you like modern style life, you can have many places of interest in Hangzhou. Enjoy the good food and very large business companies here. So this is the Hangzhou. And talking about Westlake University, it is a new university. It has been established only 2 years ago. Our target is to, by 2026, we attracted around 300 principal investigators, from assistant professor to chair professors. Currently, we have only less than half, like only 140 something assistant professors here. And we have only three schools, which are School of Life Sciences, School of Science, and School of Engineering. So we are basically tiny universities. Currently, we only attract PhD students. We have only 600 PhD students right now, but by 2026, we would like to attract also undergraduate students. So I know today many PhD students and postdocs are joining the seminar here. I know most of you will looking for jobs in future. So Westlake University can offer you very good opportunities for your career development. Personally, I welcome you, most welcome to send up your application to Westlake University and join us. Okay, so this is our new campus. It will be established by 2021, next year. By the end of next year, we are going to move into this campus. The unique of this campus is you can see a ring. We call it academic ring. The idea of this ring is to connect all the three schools together, like the School of Science, School of Life Sciences, and School of Engineering. So you can go to anywhere of this campus without leaving the building. And this is if we count it as a single unit architecture building, this is the biggest one in China of the single unit. Okay, that's our new campus. And okay, so let's move on to the presentation today. I will talk about 4 parts. And first of all, today's presentation will focus on the transistors on 2D semiconductors. So why we are care about the transistors on 2D semiconductors? If we look back of the history of the computing, the first computer has invented in 1964, and it has big, like occupy 150 square meters space. And after 50 years, we have iPhone 6. This is everything has been shrinked to a size of like this. And in future, these days we've been focusing on the quantum computing, AI or cloud computing. These are the future of the computing. And currently, we are at the technology of 5 nanometer node. And recently, both Huawei and Apple has released their new processors. They are based on the 5 nanometer node technology. And the the transistor has been developed from the planar transistor architecture to FinFET right now, and in future, the Samsung has proposed the gate-all-around architecture, FET, and all this development required based on the silicon technology materials. And however, we all know the very famous quantum tunneling of the silicon materials. Anything below 3 nanometer will be a challenge in future. So that's the reason we focus on 2D materials. Besides on the exceptional optical and electrical properties of the 2D materials, the ultimate thickness of the 2D materials gives us the actual advantage. In terms of the transistor, we can build a transistor with a channel length as small as of 1 nanometer without the quantum tunneling. And in fact, we have people have demonstrated already the gate length around 1 nanometer transistor on monolayer MoS2, bilayer MoS2 transistor, and they achieve already a decent on-off ratio, 10 to the 6. Okay. However, there are many challenges before the 2D transistor can be used in practical. Today, we're going to focus on two parts. One is the high quality contact. The other part is the bipolar conduction. So we all know the transistor has a large contact resistance between the 3D metal and the 2D materials. The reason is there's a Schottky barrier between the 3D metal and the 2D materials. If we do a little review and we plot the contact resistance as a dependence of the materials quality or material sheet resistance, we can realize that for monolayer 2D materials, in order to reduce the contact resistance, the way is to have a better, more conductive materials, or in other words, to reduce the sheet resistance of the materials. However, we would really like to pursue using the same materials, but reduce the contact resistance. In other words, to moving down the curve. Currently, the only way to move down the curve is to increase the layer number of the materials from 2 layers, 3 layers, 4 layers, and 5 layers. And what we are really care about is whether we could move down the curve on monolayer transistors. Okay, so this is the first challenge. The second challenge we are facing now is, in theory, if we can tune the metal contact, the work function of the metals by choosing different metals, like low work function metal, we would have the N-type conduction. If we choose a large work function metal, we would have P-type conduction. However, in reality, no matter what metals we use, all the Fermi level has been pinned to a certain level. So we cannot observe the bipolar conduction for certain materials like MoS2. So this is the second challenge. And people have demonstrated many strategies to overcome these challenges. For contact engineering, we have demonstrated, the other researchers have demonstrated the edge contact geometry, or by inserting turning layer, or by using the phase transition materials to form the metallic and the semiconducting interface. Or recently, people have demonstrated the van der Waals contact between the metal contacts and the 2D layer by using the metal transfer technique. Okay, all of these methods can improve the contact quality 2D materials, 2D transistors. In terms of the bipolar conduction, people using doping or defects engineering to achieve the bipolar conduction, like the chemical doping of the MoS2 to achieve a P-type doping, or using the plasma doping techniques, and recently using the laser-induced doping, and the oxygen atom doping. And this year, the people demonstrated that using electron beam to dope the multi-layer MoS2 devices to P-type doping. So this is all very interesting techniques. Okay, for our solutions, we propose to use the thermochemical scanning probe lithography technique to improve the quality of the contacts and also to achieve the bipolar conduction on MoS2 transistors. Okay, a little bit review, a little bit introduction of the scanning probe lithography. It has been developed in 1995 in the Millipedia project at IBM. And the idea is to introduce a resistor at the end of the cantilever, and by flowing a current, the resistor can have accumulated heat that can be transmitted into the tip of the cantilever. So by the strong interactions between the tip and the polymer, we are able to create nanostructures on the polymer, and then we can further transfer the nanostructures into the substrate of choice. Okay, because we are using a thermal mechanism to introduce this nanostructure, we call it thermal or thermochemical scanning probe lithography. And of course, depending on the mechanism we are using, there's many different types of scanning probe lithography techniques, like physical or chemical mechanics here. Okay, so for scanning probe lithography, to improve the contact quality, we developed a multi-stack lift-off process by using the PPA and the PMGI two-layer process. We are able to create, firstly, is the nanostructure on the PPA layer by using the thermal tips. Then the good advantage of this process is we could image the 2D layer in situ, and then we put on the electrode by using the overlay function. This is precise and wouldn't need any markers. And the more important is the PPA polymer can be evaporated completely without any residues. And PMGI has also very unique features. When we do the undercut etching, the PMGI can also be removed completely if we look at the surface quality after processing compared to the electron beam lithography, which we normally observe the residue of PMMA. After, in our TSPL method, we can greatly preserve the quality of the surface. And because the tip can never touch the materials, we wouldn't have any damage to the surface. And one unique feature is in this process, we actually introduce certain doping effect in the contact region. That's another very important reason we can improve the contact quality. Okay, by using this lift-off technique, we fabricated both back-gated and top-gated transistor on monolayer MoS2 flake, either from the exfoliated sample or from the CVD grown sample. So if we look at the results, we can see the on-off ratio we achieved on monolayer MoS2 is as large as 10 to the 9, and we can achieve the SS factor to up to 64 millivolts per decade. These are very good numbers for monolayer transistor. And if we do the temperature dependence transfer curve, we can observe the metal insulated transition. And we also observe the linear IV curve even at the low temperature. This is a good indication of the high quality contacts. Okay, so let's go back to this curve and to see whether our lift-off technique can bring down the curve. So this is the result for one layer CVD sample. You can see clearly we actually bring down the contact resistance at the same sheet resistance of the materials, and we further reduce the contact resistance by using a more conductive materials from the exfoliated MoS2 monolayer. And as you can see, we bring down the trend around 1 order of magnitude. And in future, this is the requirement for the industrial application. We still have some room to improve, to further improve our the quality of the contacts. Okay, so to demonstrate the versatile of our method, we also fabricate some transistors on tungsten diselenide. These materials are very famous. It's very challenging to make good contacts. However, we still can achieve very good n-type conductivity in one layer tungsten diselenide, and the on-off ratio is up to 10 to the 8. And we also observe the linear dependence, IV dependence on this monolayer transistor. It's a good indication of our method is universal to other 2D materials, not only for MoS2. Further on, we demonstrated the large-scale patterning capability of our lift-off process. You can see this is a whole bar structure. The scale size of this devices is like 1 millimeter scale. And another capability we demonstrated is the etching of the materials. For example, this one, we made a inverter. So the first step is to etch the triangle MoS2 monolayer into this rectangular short channel. And then by using the special overlay function, we can precisely align our electrode with the rectangular channel to form a inverter. Okay. In terms of the resolution, we could achieve so far the minimum resolution is 13.5 nanometer. This is a simple liftoff method, and we are working on the hard mask liftoff method, which is supposed to give us resolution below 10 nanometer. Okay. So that's the first example by using thermal scanning probe to make good contacts. The second example I'm gonna show today is to using the same technique to dope the materials in order to achieve the bipolar conduction. For now, we instead of using the PPA polymer, we use the scanning probe, heated probe, to interact with the 2D layer directly. Okay, as you can see here, by introducing certain gases, by control the gas environment, after patterning, we could see in topography, we did not introduce any changes, which means we maintain the topography of the materials. However, if we test the Kelvin probe force microscopy, the KPFM, which is consistent with the Fermi level, we can clearly see a dip in the patterned region. It means the heated tip actually introduce the doping into the 2D layer and tune the position of the Fermi level. And in this case, we introduce the p-type doping in the 2D layer. And this is a dependence of the doping level as a function of the patterning parameters. Here is the scanning speed, okay? And we use the Raman spectrum to characterize whether the p-doping has been achieved after the patterning. So besides Raman spectrometer, we also use the XPS to determine what is the mechanism of this p-doping. And as you can see, we'll compare the XPS spectrum for the pristine sample and the two samples heated at certain temperatures, okay? And we observe, in order to fit the XPS curve, we have to introduce extra two sulfur atoms here. So we propose in the MoS2 matrix, some sulfur bond can be broken and leave a sulfur vacancy, and also these sulfur atoms can be attached to the pristine sulfur atoms here to forming this kind of particular sulfur-sulfur bond. Okay, and this is the sulfur-sulfur bond is responsible for the observed p-type doping. This is our proposal. And after the XPS measurement, we did the DFT calculations by introducing different numbers of this sulfur-sulfur bond, like 1 sulfur bond, 2 sulfur bond, and 3 sulfur bonds. We calculated the DFT results and to keep tracking the evolution of the valence band maximum. And you can see, as we increase the number of the sulfur-sulfur bond, this valence band maximum is shifted towards to the right, and this is corresponding to the Fermi level shifting downwards, like corresponding to the p-type doping. Okay, so far we have used the Raman spectrometer and XPS and DFT, and after that we use the TEM to basically observe whether there's this kind of sulfur-sulfur bond in the atom matrix. And as you can see here, we can see some contrast in the lattice, and we identify this contrast as the S3 contrast. This is the evidence of the SS bond can be observed in the TM image. And by comparing the different images of the different locations, the concentration of this sulfur-sulfur bond is determined around 3% to 4%. Okay, so far we're using the scanning probe lithography to demonstrate the p-type doping, and then we can simply change the environment chamber to different gases. For example, here we're using nitrogen gases. Instead of converting the materials to p-type doping, we introduce the n-type doping. Okay, this is the n-type doping level as a function of the tip temperature or the heater of the temperature of the heater. As you can see, we can achieve the continuous n-type doping while we're doing the tip scanning of the sample, and we also use the n-type, the Raman spectrometer to characterize the n-type doping has been achieved in the materials and also the XPS. And it is well known the n-type doping is a result of the sulfur vacancy. So we believe by using the hot tip to scan the sample in an inert environment, we are creating more sulfur vacancies, and these are the reason for the further n-type doping of the MoS2. Okay, so far we are able to achieve both n-type doping and the p-type doping by simply tuning the gas environment of the chamber. So the next step we could do is a p-n junction. So firstly, we prepare a pristine sample and we dope the entire channel to n-type, and you can see the transfer curve. The threshold voltage has been shifted to the left. This is a proof of the entire n-type doping of the channel. And we also did a p-type doping of the entire channel. Compared to the pristine transistor, the p-type doping transistor, the threshold voltage has been shifted to the right. This is also consistent with the entire p-type doping. So far, we are able to prove that our scanning probe lithography n-type doping and p-type doping are both working in a real device. So the next step, we patented a p-n junction by doping only half of the channel into p-type and the other half of the channel into n-type, and we can create it. We have created a p-n junction on monolayer MoS2 transistor, and if you look at the IV curve, we can observe a very considerable or significant current rectifying. And if you look at the rectification ratio, the ratio is as large as 10 to the 4. This is the largest ratio in monolayer MoS2 transistor diode. Okay. So if we further look into the p-n junction we have created, as you can see, this is a KPFM image. The S-grown sample has a uniform CPD value, or the contact potential value. After the p-n junction doping, we can see a contrast between p-type, p-doped region and n-type doped region, and this is the p-n junction here. However, this rectification ratio of the current is also a dependence of the backgating. So if we plot the rectification ratio as a function of the backgating, we can see for the p-n junction, there is a peak at certain backgating. So how to understand this phenomenon is in our devices, there are two mechanisms. One is the p-n junction, one is the p-n doping introduced by the scanning probe lithography. The other mechanism is the doping introduced by the gating. The gating is like a kind of universal doping to the entire channel. So there's only one point where the TP-induced p-n doping dominates the junction. So that's the position here. Once we increase the backgating to like a large n-doping, the junction will be disappear because the universal doping dominates the channel. Then you would have a symmetric IV curve eventually. So if you look at this IV curve here, at the negative small backgating, the TP-induced doping dominant, you get a symmetric IV curve. But once we have a large backgating, this IV curve turn back to symmetric. Okay, this is another proof of the tip-induced p-n junction doping. Because the p-n junction, there's another unique, interesting property is the photocurrent. So we also demonstrated the photocurrent at different backgating. As you can see, still at the very like small backgating conditions, like -35 volts, we can get the huge light current and dark current. The difference, the ratio is as large as around four orders of magnitude. And once we increase backgating, this dark current and light current are they're almost the same. Only at this point they have the largest contrast. Okay, so if we further plot the light and dark current ratio as a function of the backgating, we still observe a similar phenomenon that there's only one peak here at certain backgating, that the tip-induced p-n junction dominates, that we have the strong p-n junction only at this point. If we plot also the rectification ratio into the same figure, we can see that they are basically consistent here. And this is the reference for n-doping, purely n-doping transistor, that you have no peak, and this current ratio and the rectification ratio are almost the same. Okay. Okay, the last part of my presentation will be introduce the TSPL, scanning probe lithography technique. So the important part of this technique is the cantilever. In our research, we use two types of cantilevers. This cantilever is made by transistors here. We introduce like certain different doping level of the silicon, and here is a low doped silicon which has a larger resistance. When flowing the current, the heat will be accumulated here and transmitted into the tip. And this type of transistor is still using a laser as a laser diode as a like the sensor to determine the positions. And this transistor is developed in NanoFrazor, and they use two resistors. And by eliminating the lasers, it can reduce the tuning of the laser part. And one sensor is used for the topography sensor to locate the position of the tip. The other sensor is the heater that can accumulate the heat into the tip and pattern the polymers here. So this is a key part of the scanning probe lithography. Okay. And one feature I would like to show here is the closed loop lithography for NanoFrazor. Let me have to go to here. So if you look at this image here, when the tip is patterning the polymer from the left to the right, we turn on the heater that the polymer can be patterned. But when the tip is scanning back from the right to the left, we turn off the heater. The tip is behaving as a normal AFM to map the structures we have just patterned. By comparing the structures, we could introduce the computer assistant programming parameter optimization in order to achieve the best closed loop lithography. And this is an example by comparing. As you can see, the first few lines, the fabricated structure has a difference compared to the design. But after a few pixels, you would have self adjustment of the parameters, and then we get a perfect image compared to the design. Why this is important? Because in certain applications, this 3D patterning is very critical. Can give you an example here. So normally the process is we pattern structures in the PPA polymer here, and the structure will further transferred into the silicon by either etching mechanisms here or by the lift-off to create some additive structures here. And this year, a group using the NanoFrazor to pattern the Fourier surface in silver materials, and by only using the 3D pattern capability, they could achieve this plasmonic resonances for single unit, but at 3 resonance wavelengths. This is very it's not possible if without this 3D patterning capability here. And besides this 3D capability, there's many other interesting paper I would like to share with you. Is using NanoFrazor to directly cut 2D materials. The Dr. Xiaoliu and Professor Brugger from EPFL, they very smartly put the 2D layer on top of the PPA layer. By using the tip to hit that PPA layer, they could cut the 2D materials directly, or they could introduce the strain to modulate the band gap of the 2D material. This is very smart ideas. And other papers on the precise location, positioning of the sub-nanometer nanoparticles using NanoFrazor. And this is 2 good review papers if you are interested in the technique of the thermal scanning probe lithography. Okay, so this is the end of my presentation. I'd like to show you a few images here of the instrument I've been working before. This is the NanoFrazor prototype instrument in IBM research lab. And again, this is the prototype NanoFrazor system. This is the modified AFM system in Professor Elisa's group at NYU. And we modified the Brooker AFM and the Angeland's AFM to create the scanning probe lithography technique ourselves. And this is my lab. I joined Westlake in September this year. This is our lab. This is a new campus. I went to the new campus, and the position here, where I stand here, is the clean room part. I will put the scanning probe, the scanning probe system into the clean room. And this is the laser, direct laser writing system in our lab. And as Felix mentioned, there's a NanoFrazor Scholar, hopefully shipped within this week, and I would expect to receive it pretty soon. So what I want to emphasize, mention here, I went into this project in 2017, and after 3 years, I have very fortunately, I have my own lab. It's a very, I have my good luck. I wouldn't think about my own lab back in 2017 and have my own NanoFrazor, but today I have everything seems true, and it's very amazing for me. Okay, so again, I would like to thank my postdoc supervisor, Professor Elisa Redo at New York University, and all of this work has been done in New York University under the supervision of Professor Redo. So if you are interested in her research, please refer to the website and her email. Okay, and finally, thank you very much for your attention. Stay well in this global pandemic. And if you have any questions, send me emails and or visit our website. You are welcome to send me emails. Okay.